Okay, let's assume that we have a parametric curve in the plane x equals to x of t and y equals to y of t. We can call alpha of t equal to x of t, y of t. If we plot several points of t, we get points x and y, and those points x and y can give us something like this. It will give us a curve in the plane. If we fix a point t sub 0, let's suppose that this is x of t sub 0, y of t sub 0, then we have that the velocity vector alpha prime of t, which is x prime of t, y prime of t, is a vector that is tangent to the curve. This is the vector x prime of t sub 0, and this is x prime of t sub 0, y prime of t sub 0. In the case that x prime of t sub 0 is different from 0, then this component, this is the x prime of, this part is the x prime of t sub 0, and this is the y prime of t sub 0. And if x prime of t sub 0 is different from 0, that means that near this point, this graph, this curve, represents the graph of a function. That means that we have, near this point, we have that we can write y as f of x. And the interesting part is that we don't need to know f of t. We don't need to do the process of eliminating the t or solving for t and replacing the other in order to compute the first and second derivative of this function. Notice that we have that y of t equal to f of x of t, right? We have this relation, and using the chain rule, we get that y prime of t is f prime evaluated at x of t times x prime of t. That means that the derivative of the function f at x of t can be written as y prime of t over x prime of t. This is the first derivative. Then to compute the slope of the tangent line, we just need to compute y prime of t sub 0 and x prime of t sub 0. And somehow it makes sense because the slope of the tangent line is this over this, which is y prime of t sub 0 over x prime of t sub 0. If we call this function g of t, then we can compute the second derivative. The second derivative, using the same thing, the same argument, the second derivative evaluated at x of t would be g prime of t over x prime of t. Then this is the expression for the first derivative, and this is the expression for the second derivative. Let's do an example. Let's suppose that x of t is 2 plus t squared and y of t is 3 minus 2t. If we solve for t, we can see that t is 3 minus y over 2, and if we replace, we notice that the x is something in terms of y squared. That means that this is going to be a parabola that opens to the left. But let's compute the first and second derivative. We have that in this case, x prime of t is 2t and y prime of t is negative 2. Therefore, f prime at a point x of t is going to be negative 2 over 2t, which is just negative t to the negative 1. Also, if we want to compute this is the first derivative. If we want to compute the second derivative of that function at x of t, we call this function g of t. Right? This is the function g of t. And then the second derivative would be the derivative of g of t, which is negative 1t to the negative 2. That means that t to the negative 2 over x prime of t over 2t. And that means that this is just 1/2 t to the negative 3. Let's pick a point to see this graphically. We pick t equal to, let's say t equal to 1. Right? Then if t is equal to 1, the point x is 2 plus 1 squared is 3, and y is t equal 1, it would be 1. That means that we are at the point 3, 1. We have here 1, 2, 3, and here 1. And this is the point. Then the first derivative of the function f prime at this point actually would be x prime of x of 1. X prime of 3 would be, t is 1, it would be negative 1 to the negative 1, it would be just negative 1, right? Negative 1. That means that that function, it has a slope negative, it goes like this, right? Slope negative 1 is going down. And let's see the second derivative. The second derivative at x of 1, the second derivative at 3 would be 1/2, 1 to the negative 3 is just 1/2. That means that that function is concave up. Then most likely the graph of the function will be something like this. We have that's the graph of the function. Let's see if we can solve for eliminate the t and see how this fits into the whole graph of this parabola. If we solve for t, we will get from there that 2t is 3 minus y, and that means that t is 3 minus y over 2. And then the x would be 2 plus 3 minus y squared over 4. We can see that this parabola, when you think about x, it opens to the right. I think I was wrong at the beginning, but then this opens to the right, and the minimum value is 2, and that happens when y is equal to 3. We have 1, 2, 3. The minimum value is 2, and the parabola opens to the right. Then the parabola looks like this, right? This is the vertex of the parabola. It goes like this. But in the study that we did, we didn't need to know this relation to find the first derivative and the second derivative of that function. Here is the function, it goes like this. We were analyzing at this point, at the point 3, 1, because t is equal 1. We were doing everything at this point. Okay, but then the point is that we don't need to solve for t, eliminate the t in order to find the first derivative and the second derivative of the function that makes y equal to f of x. We don't need to know this function to compute the first derivative and the second derivative. If we have that's the parametric equations, that's enough to find the first and second derivative.